All right, thank you very much. I hope you don't mind. I'm going to use this mic. If you need me to speak louder or quieter, please let me know. I'd kind of disappear behind that podium. So today I want to tell you a little bit about some of our work in trying to create very small-scale robots and using microfabrication for robotics in general. And so I always like to start off a presentation by talking about what I mean by a microrobot. Let me see if I can get this thing to work. There we go. So what I mean by a microrobot is this guy. So, oops. So this guy, a little ant, you're talking about something that's millimeters in scale, but certainly has very, very small features inside of it. So how do you make something like this? Well, ultimately, what I'm going to be talking about is this guy that I'm going to show you a little bit later in where we're moving with something like this. But for now, the kind of specific definition that I want to talk about for a microrobot is something that's ultimately millimeters in size, but generally micron features. So that generally involves some kind of microfabrication in order to make it. Mobile, the mobile part of the phrase, I want something that's truly mobile, right? I don't want something that takes me all day to get from here to the edge of the stage, right? That's hardly mobile. I could stomp my foot and a piece of dust could make it that far. So I want something that could move body lengths per second. You know, ants can move, tens of body lengths per second, really, really impressive creatures. And we ultimately want to get something as dynamic as that. So we also want the ability to move through different environments, so be able to move across this kind of carpeted stage, the wood floor, the pavement, cobblestones outside. So be able to move through, the grass, dirt, et cetera. All the things that this little ant can do, we want to ultimately be able to do as well. We have this wonderful existence proof in nature, as was mentioned yesterday, of the ant. And then autonomy, I add a question mark next to. So there's some question as to how much autonomy you also actually want on board your little robot. Ultimately, for me, I want some rudimentary form of control, some decision-making, ultimately capabilities, at least to the scale of what the ant or a termite or something can do. And sensing on board, so in order to do that. And obviously, I want power on board as well. So having to deliver power remotely, is fine for kind of the initial stages of the work, but ultimately we want something where we can have power on board as well. So when we're designing parts of this robot, we want to think about efficiency and stuff when we do that. And then the other big question that was mentioned in Ricard's talk yesterday is this kind of swarm behaviors and communication between robots, and ultimately what kind of things, maybe you can't do something very impressive with a single one of these robots, but with a whole group of them, you can do some very impressive things. So ultimately, some form of communication on the robots would be nice as well. So how close have we come to this? Well, there's a very famous paper that many of you may have heard of, some of you probably not, by Richard Feynman. It was actually a talk that he gave in 1959 called "There's Plenty of Room at the Bottom." And the whole idea behind this is we've been thinking big things, solar systems, et cetera, but there's a lot of things to discover and to make and to engineer at the very small scale. And so as part of this talk, he talked about tiny hands building tiny hands building tiny hands. And so that's kind of first mention I can find, at least, of microrobotics in the literature. He gave another talk called Infinitesimal Machinery in 1983, and this was kind of as video games were starting to become more popular, and so he had the idea of a video game where you could sword fight a paramecium, basically. So you would have a little robot that would sword fight a paramecium, and so that's maybe more similar to the definition of microrobot that I provided earlier. And then in 1987, you had people like Anita Flynn, who was in Rod Brooks' lab at the time, coming up with the idea of gnat robotics. And so this was also the advent of MEMS, microelectromechanical systems. You could make small motors for the first time, small sensors, all in the same processes that you use to make integrated circuits. And so people were thinking, I can do all of these things at once. I can make sensors, motors, circuits, power. I can put it all together and make a little robot. And so this was kind of the idea. There was probably a pretty big delay until the first of these started becoming realized, but there's kind of been an explosion over the last decade or so, I'd say. So this is the only robot right here that's actually walked. This guy, I'll show you in a bit, did some pretty impressive push-ups. This is a really little guy by Bruce Donald's group that kind of scooted around. iSwarm you saw a little bit yesterday. That was a big European project. There's a lot of magnetic robots, both in Brad Nelson's group in Zurich and Metten City's group, where you use Helmholtz coils to steer little magnets around. In this case, this was designed to steer through your eyeball and deliver drugs to the back of your retina. Still seems a little freaky to me, honestly. And then you have things like Rob Wood's RoboBee, which is a little bigger than the definition, but still pretty cool, so I lumped that in there anyway. And then some of our work that I'll talk about toward the end. And this is not to scale at all. I mean, I think all of this fits up in this little corner right here. There's a huge amount of white space still before we get to that ant. And so that's ultimately what we're trying to do. So here's a robot that I worked on when I was a graduate student at Berkeley, and I think it's still a pretty impressive thing to see. So what you're looking at here are two little L-shaped legs. This is a little slider crank mechanism. The bright spots are hinges, so these legs are kind of moving up and down like this. And then you have a roll cage kind of around the legs right here. So what you're watching in this is completely autonomous, so this was solar powered, completely autonomous Microrobot push-ups. But ultimately, we want to be able to move beyond the Microrobot calisthenics into something a little bit more interesting. And so this is the full robot that you saw here, and the question is why this is really hard ultimately to do, and why it's an interesting challenge to tackle. So this is what you saw in the little video right there. The whole thing is about 8 millimeters by 3 millimeters by about 1 millimeter thick. So these were the legs that you saw. There's motors up each side. This is a whole bunch of solar cells hooked up in series to give you high voltages for the motors, and then a little CMOS sequencer in the back. So there were no sensors on this, but it was kind of a little finite state machine to have this guy crawl around. Ultimately, it kind of scooted to the right over about 8 minutes, and so the main graduate student working on it said, woohoo, I graduate, and left. So we still had a lot of stuff to do on that. So why is it so hard? Well, one thing that I'll say is that one of the big challenges is the mechanism. So this guy, if you looked at it funny, or certainly if you sneezed on it, shattered. It was very, very fragile. A lot of that comes down to the materials that were used to make it. So a lot of silicon, polysilicon parts. The hinges that I talked about were 2-micron square polysilicon pin hinges that were incredibly fragile. You put it in the box, and the legs would rip off just due to the electrostatic forces. So mechanisms, we need much more robust mechanisms, and the mechanisms to support the kind of locomotion that we ultimately want. Motors were ultimately the failure point of this robot. We ultimately didn't get the power density and the forces that we needed in order for this robot to pull itself forward. And then mobility is another big challenge. Even if it had been able to walk forward, it just kind of pulls itself along, kind of limps along, and isn't able to actually turn or do anything kind of interesting, and it would move very, very slowly. So we ultimately want locomotion and mechanisms and motors that support locomotion that allow us to move much more dynamically, like the biological inspiration that we have. So in addition to mobility and mechanisms and motors, another big challenge is integration. So I mentioned earlier this big idea that we could make everything in the same process, all the motors, all the sensors, all the mechanisms, all the circuits. Turns out that's really hard to do. Not necessarily really hard, but not necessarily the best way to do things anyway. It's better to make motors in a good motor process, sensors in a good sensor process, circuits in a good circuit process, and then somehow integrate them all together. And in this case, I also kind of lump control and perception and all of the other things that we ultimately want to have on a robot of this size. So how do we both mechanically and kind of control-wise hook all of these parts together to get some interesting behavior? And then the elephant in the room, of course, as many of you are probably thinking, is power. So how are we ultimately going to power these robots? The problem that we have is a scaling problem. As we're scaling down in size, right, our energy is scaling down kind of as L cubed, basically, as the length of the thing cubed. And so it's hard to power, a big robot for very long. It's going to be even harder to power a very small robot for very long. So that's a big thing that we need to think about. So what I'm going to talk a little bit about today is kind of the goal in my lab is combining some of the expertise we have in microfabrication along with some inspiration from biology in both creating very small robots, which is primarily what I'll talk about, but I'll also mention a little bit about the things that we're doing to hopefully improve and enhance larger robot capabilities as well. So the kind of brief outline, I'll talk a little bit about what we're doing on the mechanism side, basically expanding the materials toolbox that we have to work with in creating these mechanisms at small scales. Motors, I primarily talk about electrostatics, and I'll talk a little bit about chemical actuation at the end, and how we do this efficiently and still get the power densities that we want. Mobility is one of the things I'm most excited about right now, and basically strategies to determine both effective and efficient locomotion at very small scales. We have a good idea of how to make things move at larger scales, but when they're very small, it's much harder to make them move. So, and then finally, I'll talk a little bit about integration, basically connecting all of the pieces and adding perception and control for the first time, even in its most rudimentary form right now. And then I'll talk a little bit about power in a couple different spots as well. So I'll start with mechanisms. And what do we want in our mechanisms? Well, this is a video from Bob Full's lab at UC Berkeley, and it shows a cockroach, which is a little bigger than we ultimately want, but gives you the basic idea of what these insects can do. So this is obviously very rough terrain, and what you see is a cockroach just running through this terrain willy-nilly. It doesn't really care, but it's stable. It doesn't flip over. Imagine one of your big robots trying to get through, similarly sized terrain to this. It's really tough, right? Or if you're trying to get through it, right? You're trying to see, okay, I want to step here, and then I want to step here. One of the nice things about a cockroach is it actually has mechanically tuned legs to provide part of the control system so that it's able to do things like this. So we want this kind of ability to have compliance in our system and this tuning in order to get stability through our mechanisms as well. So another big thing that we want, or one of the interesting kind of forms of locomotion that I like at small scales, is jumping. So the ability of these small insects to be able to do things even like jump out of water there is pretty impressive. And the way these insects do that is they store energy slowly and release it very quickly in order to jump. And a lot of that comes through the addition of compliant mechanisms as well. And so ultimately what we want out of our mechanisms in order to get these kind of locomotion ideas is compliant mechanisms and material diversity. So these are obviously made of hard and soft materials. And having those hard and soft materials in our robots, I think, will help us a lot as well in creating these kind of impressive locomotion feats. So if you look at kind of the state of the art with this, so on the left right here, you see a close-up of the push-up robot that I showed you earlier. So these are the 2-micron cross-section polysilicon pin hinges. Your hair is 50 to 100 microns for scale. So just incredibly fragile. It all comes from traditional micromachining processes, which means silicon and silicon derivatives, which are very brittle materials. And so we like that because it gives us the small features that we ultimately want, but the challenge is that we're limited in our materials that we can use. At even a slightly larger scale, so this is Rob Wood's work, both when he was at Berkeley and has continued at Harvard, of this kind of lamination process. You have a lot more materials that you can play with, even as still limited subset, but you have a lot more materials than you can do at the microfabrication scale. And obviously, if you go bigger than this, you can imagine using all sorts of materials, right? You just go buy them and slap them on your robot when you're talking about bigger robots. So at these scales, everything is very challenging and small, and ultimately we want small, but the material diversity that I was talking about. So we want to expand this materials toolbox. So how are we going to do that? Well, what we effectively came up with was a micro-molding process. So I'll show you some MEMS cross-sections, but hopefully they're fairly clear. So the basic idea is we start with a silicon wafer. So the same thing that you do for IC processing. In this case, we start with a 4-inch wafer, so we can make a lot of these little robots at once. It's all batch fabrication. We etch trenches. We basically do a cookie cutter etch into the silicon here. So we create these trenches. They can be very high aspect ratio, something like 20 to 1. After that, we refill that with a polymer of our choice. Usually we use a silicone elastomer. So we refill this. We can create these trenches down to 2-micron widths in our lab as well, for reference. So this little one at the end here is 2-micron wide, and then about 40 microns deep. So we clean off the surface, and then once we've cleaned off the surface, we can do more lithography steps or more etching steps. So then we can etch and define silicon features. So we have silicone and silicon, so hopefully I'll keep that clear. So the blue is the rubber, the gray is the silicon. And in this case, we've used a special wafer that's called a silicon-on insulator wafer. So it has a silicon layer, an oxide layer, silicon dioxide layer, and then another thick silicon layer. So we need to remove some of the oxide, so we dunk it in hydrofluoric acid for a short bit, remove the oxide, and now we have things like springy bands where we could store energy for a jumping robot. We have compliant hinges for legs and stuff like this. So it actually works pretty well. You get good adhesion. You could do other things to promote adhesion. We've done some mechanical testing of these things. The nice thing about microfabrication is that you can basically build and design your tester into the same process. So we have basically these big motors that pull on this little piece of rubber here. So this whole thing was about 20 microns long. And what we end up finding is that it's very consistent. So all of these lines right here kind of follow the same path. These were all for different samples. And then we find that our hydrofluoric acid dip at the end kind of softens our rubber a little bit as well. So those are good things to know. And all of the steps preceding that probably harden the rubber a little bit, cross-link it a little bit more. So there's some interesting kind of characterization that we can do. But I think of more interest to you is the fact that we can now make things like little legs. And one of the things I mentioned earlier is I really like the idea of jumping robots at this scale. So we can make little energy storage things for little jumping mechanisms. And so this is a very weird video for anybody who's done any MEMS things because you're not used to seeing strains like this in a MEMS device. So this whole thing is about 3 millimeters on a side right here. So these are the little rubber bands that you can see in that video. And this thing is going to be compressed and released in order to show that we can store enough energy for a jump. So right now there's no motors on this, there's no power supply, no control. So it's very, very simple. It's just a mechanism right now. So the actuation we use is a very fancy actuation method we have in the lab called graduate student with tweezers. So the graduate student in question is going to use the tweezers to compress this and release it in order to get a jump. So what you'll see in the next video is a black fuzzy dot flying through the air as we get this thing to jump. So there goes the black fuzzy dot right here. This is Aaron Garrett, the graduate student with the tweezers. You can see this thing bounce on the table. The same device is used over and over until we ultimately lose it. You can see it kind of fly off the screen at some point. But it bounces around, incredibly robust, and ultimately we were able to get, jump heights of, 100 times the robot size. So it was kind of a nice demonstration that we could do things with these new processes, with these new materials, to make mechanisms to allow really nice locomotion in small robots. So we can do a lot of other things with this process as well, and this has become kind of a cornerstone process in our lab. So we can add more materials, so we can do extra etches and refill with new materials. So maybe we use a conductive elastomer, maybe we use an elastomer with magnetic particles in it. Maybe we use something else entirely, maybe a polymer with more damping in it to get our kind of control that we want. So there's a lot of kind of cool things that we can get, and we can make multifunctional mechanisms with this as well. So what kind of things are we doing with it in the lab? Well, we're making, I saw some nice work on sensors yesterday. So we can make kind of normal pressure and shear pressure sensors with this. In this case, we make little capacitors with both a conductive elastomer and a dielectric elastomer. In this case, we can make these gaps here on the order of microns. So we get very high capacitances in very small areas. And we can make some interesting things as well, where we have these kind of corrugated shapes, so we get more capacitance in smaller areas yet again. So there's some nice kind of sensor stuff that we can do, where we can get very high sensitivity, entirely compliant sensors with this. Another fun thing to do with this that's robotics related is looking at electroadhesion. So we saw some nice gecko adhesion work yesterday. In this case, we're doing the same thing, but now we are creating our kind of electrodes here. We have our dielectric, our kind of thick PDMS here, and then we coat this with parylene, which is a conformal polymer coating that you can do at room temperature in microfabrication, but we can do this only microns thick. So electroadhesion in the past has typically been done at kilovolts. In this case, we can do this at 100 or 200 volts, and that's something that we can actually design very small circuits to give us. So there's some cool stuff, I think, that ultimately we're doing in this case. And the best with this microfabricated version yet, which is completely unoptimized, very early stuff, is about 78 kilopascals of shear pressure at 200 volts on glass. So that's about a quarter to a third of the highest kind of gecko stuff that I've seen. But you could use this in combination, and I think it would be really neat. So those are kind of the mechanisms. Ultimately, now we want to add the motors and drive those mechanisms and make them go. So there's a lot of work in kind of small motors for small robots. Most of them are either very low forces, like I showed on that push-up robot, or they're very high power in the sense that they drain a lot of power, very inefficient. So usually they're thermally actuated, which means you shove a lot of current through it to heat something up, and that makes something bend. So that was the actuators used on the little robot that I said walked pretty well. So at larger scales, you have a lot more options in how you make motors. So you'll see why I talk about all of these in a sec. You can do things like piezoelectrics that's used on the RoboBee. You can do little elastomer-based electrostatics. You can even do things like micro rockets for thrust, or small rockets for thrust. And so ultimately, obviously, what we want in our robots is all of the high density, high forces, high power density, and efficient actuation at these kind of millimeter size scales. So it's actually pretty easy to do if you're willing to be inefficient. So this was a demonstration that we did where we made a little catapult with our rubber bands, basically. So this was all fabricated in the same process, and you effectively have a bunch of rubber bands here and then a leg around it. And so the idea is that the motors pull back the leg, you put something in front of it, and it shoots it across the room. So in this case, what you see here is there's the little projectile and the leg thruster. The greater than 7 centimeters is because we lost the little capacitor or whatever it is we stuck in front of the leg. So all we know is it went off the stage. I think it probably went much further. So these motors are done through that heating process that I mentioned. You shove a bunch of current through it and it heats. And by a bunch of current, I mean these things glow if you turn off the light. They get very, very hot. And so what you see here in this video is basically these motors. This is real-time stretching those rubber bands and storing the energy that we use to catapult small things. So ultimately, though, we want to do this efficiently as well. So we want this high power density that we get from these actuators with efficiency. And so for that, we use something called electrostatics. And so this is basically just making a capacitor. You have two plates, air in between it. You apply a voltage, and they'll move together. And so you get more force the smaller that gap is, but of course you move less the smaller that gap is. And so the solution we've come up for that is incrementally moving a small amount a lot in order to pull these shuttles forward. And so the way this works is I grab this shuttle kind of along here. Right here is going to be the thing that's moving. I grab that shuttle, I pull it forward, grab the shuttle, pull it forward, grab the shuttle, pull it forward, grab the shuttle, pull it forward. And I keep doing this. I can do it very fast. These things are very lightweight, so they have very high resonant frequencies typically. So what my student Yvonne has done is basically said, well, why do we even need these little things that grab it? So why do we even need these extra guys right here? They just basically look like big parasitic capacitors. So they kill our efficiency, and they also hurt our force density. So why don't we do the same thing with a very tiny mechanism? And so that's ultimately what he did. He created this very small little angled flexure here, and through that angled flexure was able to transmit this kind of vertical motion here to horizontal motion in driving the shuttle. And so kind of the specs that we got out of his motors a couple years ago, if you cheat and remove the backside of the motor, that just mechanically connects everything together, it's kind of dead weight, you're getting power densities on the order of 200 watts per kilogram, and I think we can get a lot higher than that. So flight muscle in an insect, just for reference, is about 100 watts per kilogram. So we can get very high power densities out of this. We can get decent force densities as well. 2.2 millinewtons might not sound like a lot to you, but it's actually quite a bit for a small robot. Measured efficiency included all of the parasitic capacitance in our setup and was about 9%, so my guess is it's more like 20. And speeds were actually kind of slower than we expected at about 5 millimeters per second. And so we actually have some really interesting kind of dynamic behavior in these when we try to drive them at high speeds that we still need to figure out in order to get them to move much faster. So to give you some idea of how these work, these are the angled flexures that you saw earlier. And so you can kind of watch these springs, these kind of cantilevered springs at the end to see the shuttle moving. And so this is at 1/10 speed, so this was filmed at 300 frames per second, just to slow it down. And so you can see this kind of stepwise motion of what we call an interim motor. We can obviously move it much faster than this. This is still at 300 frames per second, so 1/10 speed. And we can move this pretty quickly. So hopefully I've convinced you that this is actually kind of a decent route to look at for actuation in small robots. We can also do cool things. This is still made out of silicon, so we can actually look at things with our elastomer-based process as well. So the same kind of capacitors that we were making for those sensors earlier, we can also make motors out of. So instead of rigid silicon electrodes and an air dielectric, we can now use conductive elastomer electrodes and an elastomer dielectric, and we can squish that. So we can have very small gaps in between these things, and this is electric field based, so as we lower the gap, we lower the voltage required to drive the thing as well. And the nice thing about it, it's all made out of rubber, so you can squish it, you can stomp on it, and it still works, so it's wonderful. So these were made with a pretty cheap mask, so they have 20 micron gaps. So they'll have higher voltage than we can ultimately achieve, but you can see we actually got kind of the motion that we expected out of this bimorph. We apply a voltage across these two layers right here, and the thing will bend up, so it'll squish out and bend up, and these two layers, it'll squish out and bend down. So we got the operation that we expect, and what this plot is trying to show you right here is that if we reduce those gaps from 20 microns, which is this pink line, which is what we fabricated, down to 3 microns, we can actually get the same strains and displacements at much, much lower voltages. We're talking about tens of volts now for what's called a dielectric elastomer actuator because of these small gaps we can create. So, and actually, I think it's very, very exciting to kind of continue that and see what we can do. But in general, we're going to want something around the order of 100 volts, which isn't so compatible with our 4-volt batteries or something, or solar cells that we can use. So how are we going to do this? Well, I now have a collaborator named Ali Reza Khalid at Maryland, who primarily does electronics, power electronics for hybrid cars, but I've convinced him that power electronics for very small robots is a very cool thing. And so he started coming up with some ideas, and this is a very early prototype that's pretty small, but can drive those interim motors, which are typically operated at around 100 volts. And it can provide all of the kind of signaling that we need in order to drive those efficiently. So he has ideas of how to get this 80% efficient and down to 50 milligrams and all sorts of stuff. So I think there's some pretty exciting stuff to happen there. And then, so these are the motors for the small robots, but we can also think about how we could use these kind of motors or motors at this scale as control actuators on slightly larger robots, things like micro air vehicles and the like. So one of the things that we've been working on recently is looking at control actuators on these micro or nano or whatever size you want to pick pico air vehicles. And in this case, we've looked at using a tail, so another bio-inspired thing that I threw in here. In this case, we're using an off-the-shelf electromagnetic actuator for right now. And what you see here is a little inverted pendulum experiment. And so the idea is that we want to stabilize this pendulum here that's about the same inertia as the vehicle we want to put this on ultimately, and use the tail down here in order to do that. And so the only sensing on this is on the body here, so that would be on the micro air vehicle. And that's just a 3-axis accelerometer and 3-axis gyro. So to show you the thing with the controller off, because nobody believes it's actually can flop either side once he turns it on, you can actually do some pretty nice control with this. So we've done some more quantitative experiments where you kind of bang it with kind of known forces, known impulses, and shown that we can actually control it as well. And this is at 1/5 speed. So, so we've actually, I think, done some really nice things of adding these tails on MAVs as well, just to kind of prove the concept. I'm not saying you would want a tail on a quad rotor ultimately, but it just shows that we can actually perturb the quad rotor with the tail, even using kind of the smallest quad rotor we could find. So what you see here is the quad rotor flying and the tail activated there, and what you see is the little spikes that show the roll and pitch rate. In this case, I think it was the roll rate, or sorry, pitch rate is the way the tail was oriented. So when the tail flicked, you could actually see the quad rotor move. So there's some interesting things that we can do with that. So we now have like small motors, we now have small mechanisms, we're kind of continuing to work on both of those, but now the big question is mobility, is how am I going to add all of these things together in order to be able to locomote the way that I said I wanted to locomote earlier, being able to move at tens of body lengths per second, being able to move across different surfaces and the like. So we have, if you look at kind of the previous robots that are out there, and you look at efficacy, kind of step height or something that you could get out of these robots, right? The big challenge with a small robot is that everything around you is big, right? A Roomba certainly wouldn't be able to deal with this kind of step height, but you know, maybe these little cracks in the fabric up here look like that step height to our millimeter scale robot. So the push-up robot, had that been able to walk, probably would have been tripped up by a little pollen in its path. The robot that walked out of KTH, and it's a little bigger than a centimeter, it's about 1.5 centimeters long, but it was microfabricated, would certainly be tripped up by hair in its path. And then this little robot by Bruce Donald's group needs a pretty clean surface in order to move. So something like E. coli would trip that guy up. So we ultimately want to be able to deal with much larger step heights. Then another thing that we are interested in for locomotion is efficiency. So the problem with efficiency and trying to figure this out is it ends up being very dependent on implementation. So if you look at two walking robots, Honda's Asimo and the kind of passive dynamic walker by Steve Collins and Andy Ruina, they require very different powers to move across a flat surface at the same speed. So Asimo would require about 1 horsepower to do that. Collins and Ruina robot takes something like 12.5 watts. So very, very different powers based on these two different implementations. So even if we look at this in comparison to biology, so this is a data set that I kind of pulled together from the literature. We're looking at the energetic cost for small insects to move. So basically, people put insects in these little boxes and measure the oxygen consumption of the insect to calculate how much energy they're taking to move. And all of the black circles are insects. The red square, the red X's are small robots or microrobots that ultimately needed a tether in order to move. So that's not surprising. It takes something like 1,000 joules or a kilojoule to move about 1 meter. So they're going to need a tether. The blue X's are small robots that at least sort of moved without a tether. So these guys are down kind of at the top of the insect scale, but you can see we still have, you know, up to 3 orders of magnitude to go to get to the efficiency of some of these insects. So there's a lot of work, I think, to be done here. So biologists use a measure called cost of transport, which basically the energy it takes to move a given mass, a given distance in gravity. And so that's one of the things that we're looking at as well, is trying to minimize that cost of transport. So one of the big questions, if we're trying to make a small robot that moves, one of the big questions that we have to answer is how kind of models of locomotion scale, or what kind of model ultimately do we want to follow for locomotion at this scale. So we know everything from a cockroach on up kind of follows this spring-loaded inverted pendulum model. And a lot of robots, walking robots and stuff, are designed to follow that model as well. And so the basic idea is it's a mass on a spring leg, right? So I compress as I hit the ground and release as I take off. And so my center of mass kind of bounces along like this. So the problem when I'm very small is now my contact forces with the ground are pretty similar to my inertial forces, or even greater than my inertial forces from my mass, right? My mass is really tiny at this scale, on the order of 10 milligrams for the push-up robot. So the question is, at what point this model breaks down? And that's something that we have no idea of. And so there's the spring-loaded inverted pendulum, or slip model. There's also one for the kind of side-to-side motion called the lateral leg spring model. That's pretty similar. And this is a question that we're starting to try to answer. So this is all pretty preliminary work, but gives you some idea of the approach that we're taking for right now. So we're starting with a basic model of a leg. So in this case, we have 2 links for our leg. We have an active joint up here, and then we have a passive joint down here. We have some idea of how we might drive all of these things, what our mass might be. But one of the things we have is no idea of what the contact with the ground looks like, right? We have no idea of how to kind of model this. So we've tried to kind of come up with an experimental way to start looking at this. And in this case, we've created kind of a process that allows us to do the same thing that we're doing in our MEMS process with this refilling with elastomer, so we can get these multi-material mechanisms. But we do this with laser cutting, so it's fast and easy. Fast and easy to try. So in this case, we have 2 little elastomer joints here. We have a magnet, so we're going to drive this through a magnetic field to provide the active joint here. And in this case, because we only have a single control signal from our magnetic field, and we have some ways around that I'll talk about toward the end, we are creating a little kneecap and a foot to create asymmetric motion in our legs. So my knee can't, or my bottom link can't extend past this kind of straight line right here, and I have more grip in one direction than the other direction. So we expect, from our basic knowledge, for this to be kind of a stick-slip type motion. So it turns out it's a little more complicated than that. So the whole device is a little hexapod, and we set up the magnets like this, so south, north, north, south, south, north, so we get a little tripod gate through this thing. And we get locomotion that looks like this. So we can run these things on a little hot plate with a stir bar just to show the basic locomotion, and this gives you some idea of what it looks like. So we set up a test setup to do something a little more quantitative than this. In this case, we're just using a permanent magnet for now because it was easy to start with. So we have a spinning permanent magnet, and then we have our little robot moving along an acrylic sheet on top here. And so we can do this at different speeds. We've kind of come up with an optimization, assuming stick-slip and everything. And our model versus our experimental actually match very well for all of the different kind of devices that we designed. But when you look at frequency that we're actuating this at versus the average speed, the model shows something like this. Right? But the experiments show something quite different. So I think this comes down to basically our model is not that great, and that comes down to both the contact of the foot model, but also how we're modeling those springs. So in addition to being torsion springs, they're also compressing a little bit, and we're getting some bouncing in there. So to give you some idea of behavior at this kind of weird point, at the lower frequencies, it really does look like stick-slip. So the fastest we've driven these, by the way, is about 10.4 body lengths per second, I think. So this is at real time, showing something at 15 hertz, kind of in the middle there. And if I show you at a higher frequency, you see this thing is doing something a little different than stick-slip. It actually does seem to be kind of bouncing a little bit. And we're not entirely sure where that bouncing comes from yet. So we're trying to basically refine our model and come up with something a little better for trying to characterize how this thing moves. But the nice thing about this whole process is the magnets give us a really nice way to study locomotion without having to integrate our motors and mechanisms all together quite yet. And so the interesting thing as well is that some work in the microrobotics community, in kind of the magnetic microrobots, has recently shown that you can actually drive multiple different kinds of magnets independently. And so we're working with Eric Diller, who's now at the University of Toronto, to try to incorporate some of his ideas into this so we can get multiple independent degrees of freedom and ultimately really study locomotion and gait beyond this kind of stick-slip early prototype. So I think there's a lot of cool stuff we can do there. We can also make it a lot smaller. So these were centimeter cubed in size. Ultimately, like I said, we want to go to millimeters. And so we can do the same thing in our MEMS process. So we can either use magnetic particle-doped PDMS and refill our trenches with that and drive our robots that way, or we can just actually embed magnets that we buy off the shelf. You can get really tiny magnets, something on the order of 200 microns in size right now off the shelf. So this gives you some idea of a little mechanism that could ultimately be a leg. And so what we're working on right now is incorporating that into the picture that I showed you earlier of this guy right here. So this is the same as those hexapods that you saw running around earlier. So it's got those same elastomer joints, the same knee, the same feet, the same magnet right here. We're just cleaning up this process. You can see a lot of gunk here that's preventing this thing from walking, so we can actually get this to walk in the end. But it makes a pretty cool picture, I think. So there's a lot of interesting things, a lot of interesting questions, a lot of interesting engineering to answer in this mobility thing. And I think it's a really exciting area that we haven't looked at a lot yet. So finally, I'll talk a little bit about what we've been doing in terms of integrating all the pieces, putting everything together. So also mentioned yesterday was Breitenberg's vehicles. I take a lot of inspiration from this as well, in that you can get some really interesting behaviors from some fairly simple connections between sensors and motors. And that's something that we are obviously interested in when we can only make simple connections between sensors and motors. So we have kind of a fun undergraduate project in the lab that we call the Tiny Terps that we're starting to play with some of these ideas on. So we can make a lot of these little robots. They're about 1.5 centimeters cubed in size. You can pop on different sensor boards or different mobility, actually. It's a very modular system. We call them the Tiny Terps. The Terps is the Maryland mascot, the Terrapin. It's the only acronym I've come up with that I like, actually. Tiny Terrestrial Robotic Platform. So there's some cool things in there, but ultimately, like I said, we want to make these things small. So we started playing around with these guys. So this whole thing is about 7 millimeters by 4 millimeters by 4 millimeters high right now, and this is the most kind of rudimentary sensing, actuation, and control that you can think of. So in this case, we have power in the form of 2 little capacitors here. This capacitor is driving the sensing circuit, which is just sensing light. And then we have a little MOSFET here that's providing our switch or our control. And so the idea is I'm going to be detecting light, switching my MOSFET, dumping the charge in here to basically ignite my jumping actuator that will allow me to jump. And so what we're using for that jumping actuator is actually an energetic material. So this helps us a lot with our power problem as well, because we can store this energy chemically. So in this case, we microfabricate this again. So we basically etch silicon to look like Swiss cheese, so it's got a lot of surface area. We pour on some sodium perchlorate. You add a little bridge wire that's hard to see, but this little gold wire over here, it basically creates a little fuse. You shove some current through it, it heats up enough to create a reaction like this, which is quite impressive, right? So you basically get a lot of water vapor out of this reaction, so you can get thrust. So we end up putting that on the belly of the robot. The other cool thing I'll mention with this is that because we're microfabricating it, we can create little pixels of this energetic material, and we can set them all off independently as well. And so that's actually some ongoing work, is to be able to create thrust in different directions with different pixels. So we put one of these on the belly of the robot. So like I said, it's very, very simple, but it does include all of the components. And so what will happen is I turn on the light, my MOSFET will switch, and the current in this capacitor will initiate that reaction, and we'll get thrust. So you'll see something like this in the next video. This thrust was not contained. There was no nozzle on this at all, so it was very, very simple, and so I think we can do a lot better than this. The whole robot was about 300 milligrams. A third of that, by the way, was that capacitor on the sensing circuit. That was about 100 milligrams. So what you see is a big flash during the reaction. This is after Wayne turned on the light, and you can see this guy kind of spinning up through the air. The little lines here are about 1 centimeter in size. So, and then it goes up about 8 centimeters. So there's no wires connecting this at all. It's completely autonomous. And I'll play it again because I kind of like that video. So, and maybe it'll wake people up. So big flash at the beginning, and then it spins through the air. A lot of that spinning has to do with the fact that a third of the mass is on the edge of the robot. So there's some cool things that we can do with this. Ultimately, the question people always ask is, okay, that sounds wonderful, but what can I use that for? Well, some of the applications we're thinking of are being able to replace things like this. So this is a guy checking on the structural integrity of your bridge, which, you know, you're lucky if it probably happens every couple years in the US or Europe, and if it happens at all in other parts of the world. You know, basically the idea of creating small little robots that could run around and create mobile sensor networks. Obviously, to get through rubble like this after the New Zealand earthquake, you know, being small is advantageous. So maybe you dump a bucket where you have a little quad rotor fly by and drop little robots in here, and they have enough energy to radio back that they found somebody. Or you could have something like this where you have surgeons replacing surgeons with, you know, basically the small sensors, actuators, and mechanisms that I talked about at the end of a catheter. So you could do some impressive surgical tasks as well. Or termites were mentioned yesterday, building really impressive structures, right? I think they can be up to 8 meters high even, with our little robots. So kind of going from, you know, our normal method of construction to termite construction with small robots. So with that, I will thank most of the students who did the majority of the work, along with the funding agencies here, and leave you with a little cartoon as well. And thank you very much for waking up this morning and your attention during this talk. So thank you.
Okay, Sarah, thank you. Wonderful for a wonderful talk. It's time for questions. So let's see how awake you really are. Well, so to kick it off, then one thing that I was worried about is that, so you do all this amazing work developing these components, right? And actually, as you indicated yourself in the beginning of your talk, if you look at insects, there's a high level of integration across components.
Yeah.
Right? So aren't you going to face, let's say, an almost insurmountable problem at this integration stage? Because in some sense, all these components have been developed without, in some sense, the constraints, the cross constraints that come from the other components you need for, let's say, power control and sensing. So how are you going to deal with that?
So I'd answer that by saying I think we're certainly keeping that in mind, that ultimately we do want to add that on, especially the power constraint. So we think, you know, we're constantly thinking about efficiency kind of in the locomotion and the mechanisms and the actuators. The interconnections is a good question of how we're ultimately going to do that. So, you know, there's a standard wiring approach, which is just not going to be so easy at this scale, right? I mean, it's hard to wire up a large robot. Wires are constantly breaking, et cetera. So ultimately, what I think you're going to want to do is create kind of your wiring in something like your chassis and kind of add components on that. And so I think you can do integration in a fairly, I'll eat those words later, straightforward way by doing little tricks like that in order to help you do the integration throughout. So that's something that we did with the jumping robot. It was a polymer chassis with basically the circuit board lithographically patterned on top of it. So you could do something similar for the walking stuff as well.
But do you have an idea then about also the scaling of let's say, just weight, power ratios, if you start to bring these components together? Is there any clarity on that? This is a good question. So I think one of the discussions that I often end up having with biologists is how much power different parts of things take. And my argument is that in these robots, the actuators and the locomotion is going to take the majority of the power, whereas biologists often say the perception is going to take the majority of the power. It's a good question, and I think, you know, some of my background is in sensor networks, and this is something that you're constantly thinking of there, is how you trade off that power through transmitting stuff or through sensing stuff or computing on it. And so it's something that, you know, I've basically broken it down. It takes, you know, X microjoules in order to move this amount. It takes, you know, so-and-so nanojoules in order to sense this quantity, X nanojoules per instruction on a little microcontroller. So ultimately, we're going to want low-power versions of sensors and computation. Maybe we want some kind of analog circuit in the end instead of something digital. But I don't think it's I think we can do it. Based on the back of the envelope stuff that I've done, I think we can do those with that kind of energy, yeah.
But it's at this stage more a statement of, let's say, of hope. We don't really have the specifications in our hands yet that we can be sure about that.
No, we don't have the specifications yet.
Srini.
Thank you, Sarah, for that brilliant talk.
Thank you.
I had a question about the flea-like jumping behavior that you're trying to do. How can you ensure that the thing actually lands on its feet and is ready to move again?
Well, so one of the advantages you have being small, and we haven't necessarily worried about that yet, but we have thought about it. One of the advantages of you being small is that you can maybe do something a little more aerodynamically. So you're talking about Reynolds numbers of 100, 200 basically for these guys. So I think you could have little passive wings or something like that that would allow you to kind of glide in. Or do something like that. Now, if you landed on a rock and flipped over, right, maybe you'd be flipped over. Yeah, so there are small robots, small being kind of this scale. So Mirko Kovac, there's another group at Michigan State who are doing some really cute little mechanisms that allow you to both write and jump with the same actuator. And maybe we could take some of those ideas ultimately to do something like that. But I think to start, we'd go with the simple passive approach, like the Weebles wobble and they don't fall down or something like this. Yeah.
Hi, Sarah, it's Mark. I wanted to push a little more on the power thing, because you and we and others, we build these little micro robots, and they're not very useful because we're limited to the energy that we can store on board for a short time, or else you have to sort of continuously irradiate it with electromagnetic energy or something, or laser or whatever. And then I was thinking more about that and thinking, well, actually, cockroach locomotion is not very efficient compared to larger animals, but it doesn't matter, because if you're a cockroach, the world's full of food.
Right.
Well, so we need a way to get these micro robots to do the equivalent of eating, to be able. So we could spray them with sugar solution or gasoline or whatever it is, or something that they can go a short distance and then acquire energy. And I wondered if you had any thoughts about that.
Yeah, so one of the things, especially around the jumping thing that we've thought about for a long time, and once again, not had the time to do anything about, is the fact that you could go, find a nice hot spot or a sunny spot or something and recharge up. So, the bad word for that is energy harvesting. And there are some interesting things, too, that I think, maybe it is not so good for a passive, for a jumping robot because the mass is an issue, but a lot of people probably have those little watches, right, that kind of charge themselves or something like this. But yeah, eating is ultimately going to be the solution for these guys, and whether they kind of go back and eat at a power station or they can find something in their environment to do that is the open question that I don't have a very good answer on. One of the things as well is if you think about energy density, though, of your food, right? If you and I eat a Snickers bar, it's something like 20 megajoule per kilogram or something like that, whereas your lithium polymer is something like a megajoule per kilogram. So we still have kind of order of magnitude to get up to the sugar and stuff that you and I eat compared to the battery technology that's out there right now. So there's still maybe some improvement that could be made there as well. Who knows?
Tony.
Yeah, that was a great talk. Can you give me an idea of where the sort of MEMS fabrication technologies are going, and sort of how is that converging with 3D printing processes at this kind of scale? Sort of thinking all sort of embedded smart sensing people are doing now with materials. Can you start to do that at this scale, or is that?
Oh, absolutely. I mean, people are doing a lot of, there's kind of a bunch of questions embedded in there. For the 3D printing aspect and the additive manufacturing aspect, people are thinking about that at these scales. And there is things like 2-photon lithography where you can kind of, cure a polymer basically in all sorts of crazy shapes at, sub-micron scales. There are things where people are basically attracting little metallic beads and creating metallic structures in interesting ways. Some of the functional materials that you're talking about for embedded sensing and stuff, there's a lot of work in that in the biomems community, where they're interested in certain, detecting certain cells or, some kind of biological entity and sensing that and knowing what quantities are there. So there's a ton of, it's a huge community. There's a ton of work going on in both developing microfabrication processes and using now kind of standardized processes in order to make devices that are, particularly medical is a big one these days, or clinical in some fashion. Did that answer your question at all? It's a huge area. I'm not sure
Maybe you could give us a prediction for what micro-robots will be doing in 10 years.
So I usually have a slide that says that. So yeah, in kind of the 2025 timeframe. So I think certainly, at least I can say what I hope to have accomplished in that time. I think that we can have our motors integrated with these mechanisms, and I think we will get something kind of moving, whether it's at the 5 to 10 body lengths per second or something that's kind of crawling along and powered through some of the power electronics and stuff that I showed earlier. I think that is certainly doable in 10 years. Adding the sensing, adding the control or the decision making and all of that stuff I think is a little further out still. But I think people are starting to work on that kind of in parallel, and so hopefully things will come together at some point. We'll have our singularity where we have little robots running around, so who knows.
Great.
I like that
Sarah,
idea.
thank you very much for a wonderful talk.
Thank you.
All right, then I hand over now to Srini, who will be chairing our next session.
Morning, everyone. I'm Mandy.